Broadcasting live. It's America's longest running talk show on computers. It's Computer America, bringing you the biggest names in technology with guest interviews, new products, and your emails. Listen live at computeramerica.com on any device around the world. Email the show at live@computeramerica.com or find us on social media. Be sure to check out our website for contests, giveaways, show notes, live video stream, podcasts, and more. You're listening to Computer America.
Hello and welcome to the Computer America Show. We are the nation's longest running, nationally syndicated radio talk show on computers and technology. Thank you for joining us. I'm your host, Ben Crossman. And everyone, hey, I hope you're having a wonderful day and you are ready for some Computer America because we have a great show lined up for you where, time permitting, second part of the show, we will be doing computer and technology news. Lots of very interesting articles and a lot of stuff that you want to definitely stay tuned for. But in the first part of the program, we have a guest, and today's guest actually a lot of fun, and this is going to be something that you're going to be hearing more and more and more about as time goes on, and I think this may actually be a first time for a lot of you to really have the chance to listen to someone working in the field of quantum computers and actually getting a nice introduction into the possibilities, the capabilities, where they are now, where they're going to go. It's going to be a very informative show, so definitely want to stay tuned for that. But before we introduce our guests, let me go ahead and just say computeramerica.com. That is our website. There you will find a link to any articles that we do, of course, we're going to have a link to the page for everything about quantum computing. We will have any articles that we do, any videos that we show, any products that we mention, anything and everything will be in the show notes at computeramerica.com. Also, while you're there, be sure to check out the live video stream, also at twitch.tv/computeramerica. And last but not least, be sure to check out the articles. We have some new reviews up. Everyone, you want to pay attention to those, and I think that's all that needs to be said. So, as I said before, IBM will be joining us, and hopefully everything is working. So we're going to go ahead and try to get this up and running. So, everyone, let me welcome onto the show once again IBM. And before we actually do the introduction, let me just check here. So, Dr. Bob Suter, are you with us on the line?
Yes, I am.
Oh, perfect. And you come in loud and clear. That's perfect. So everyone, let me go ahead and introduce IBM. It's a company that I think everyone has, of course, heard of. But this is going to be IBM, kind of their research division, which does some of the coolest stuff in technology. And we are very happy to have Dr. Bob Suter. He is the Vice President of IBM Q Strategy and Ecosystem. And Dr. Suter, welcome on to Computer America. Thank you for joining us.
Thank you. Glad to be with you.
Our pleasure, our pleasure. So, yeah, obviously, as I was, kind of saying before, and I'm sure that you caught some of that, quantum computers, this is something that I think that pop culture got their hands on as soon as as soon as the phrase was out there, and they're like, quantum, well, that's going to change everything. And we were promised so much, and so far, I'm not saying that it hasn't delivered, but we're very much in the research phase of bringing this to market. So I wanted you to, before we get started with the topic at hand, why don't we get a bit of your background? When did you start working with IBM, and what is your background?
Well, I sometimes say that before I worked for IBM, I had a paper route, which isn't that far from the truth. I actually started working for IBM way back as a summer student when I was in college. And then when I went to grad school for theoretical math, I decided to take a leave for a while, came over to IBM, joined IBM Research. They sent me back to grad school, which I'm eternally grateful for, and spent a total of 15 years in research, then a dozen years more on the business and corporate side, and I've been back in research for almost 7 years now. I came back to lead the mathematical sciences department, and really what that meant was 6 or 7 years ago were things like optimization problems. But it also meant things like machine learning, deep learning. That is, things that are called AI today. But I think math's at the core of everything. And so I started getting involved with the quantum program about 3 years ago when I realized that it wasn't just the domain of physicists, right? So someone with just a math background, right, computer science background, could start to do something with it. And since the beginning of 2018, I've been full-time on it.
Very, very cool. And then, of course, this is this is an area that is, of course, getting a lot of attention, and deservedly so. But I think for the purposes of our conversation today, we're going to start with the basics in the beginning, and then work our way up from there, and kind of where IBM and really just the whole tech community is hoping to take these things. But basics are basics. Quantum computing.
Okay.
Tell us, what is quantum computing?
Well, I think, a lot of times we talk about comparing it to the computing we have today. And that, although it makes it sound old, is classical computing. And so the processors that are in your smartphone and your laptop, your television, your car, your thermostat, the big servers that run the cloud and the internet, those are all classical computers. And that technology pretty much goes back to about the 1940s. And in fact, they're so ubiquitous, and we've had so many decades where, they just kept getting faster and faster, and they could access more memory. Moore's law, right, which for many years said that in roughly 2 years, a classical computer would get twice as fast, twice as small, and use half as much energy. We got spoiled, right? And so with these classical machines, if we saw that there was some sort of big computing problem we wanted to go after, part of the strategy was wait, have patience, right? I mean, the computers will get bigger if we wait long enough. But it turns out that these classical computers, and again, think of your laptop. I mean, that's a good model. Mm-hmm. It's just one type of computing, right? It doesn't encompass all of those things that are computers. And in particular, people started asking in the 1980s very basic questions like, are there some things that classical computers just won't be able to do, right? No matter how long we wait. And the answer is yes. And it's yes for several reasons. The easiest example is if we think about how nature itself operates, right? So here, by nature, I'm talking electrons, and I'm talking atoms and molecules, really, the building blocks that go into really constructing, you, me, everything around us. Classical computers are really bad at approximating these sorts of things, right? So if we had a goal of saying, wouldn't it be great if we could exactly represent a molecule in a computer and how it would react? So, for example, let's imagine that you went to a doctor, he or she prescribed something for you. Well, how would that medicine actually be interacting with the parts of your body, the molecules in your body to do something? And wouldn't it be great if we could exactly simulate this in a computer before we did it for real, that is through drug tests and all these things like this.
Right. So
classical computers just doesn't work.
Yeah. So and just to jump in here real quick, I mean that little tidbit that you mentioned there, I recall when that was that they simulated a very, very small segment of space and like everything inside of it, the physics and things like that, and it was kind of still on the theoretical level. But as soon as that happened, everyone started writing these articles, and people were always asking these questions of, well, if with today's computers, back in I think 2017 was when it happened, if we can simulate just a microscopic portion of the universe in computers, couldn't an advanced society do this for our universe? And are we a simulation and things like that? I mean, wasn't that the next conclusion? It's like, well, are we a simulation? It kind of came from that.
Well, that question has been asked for probably as long as we've had computers, right? And if you go deeply into the philosophy of it all, people have been asking that sort of question for at least decades. Quantum computing, which we're talking about here, is based on quantum mechanics, which is what we were talking about with nature here. How does that really work? I mean, to give you an idea, this simulation, right? And just, to get back to your point of, well, there's something really advanced and really big and powerful.
Right.
Let's just take one molecule, right? And I use for an example the caffeine molecule, because for many people it's their favorite molecule, right? Let's face it. One single caffeine molecule, if I were to model that in a computer, the number of bits, the number of zeros and ones I would need would be on the order of 10 to the 48th. So 1 with 48 zeros. Now,
That's
put that, in context, that number is somewhere between 1 and 10% of the number of atoms in our planet. One molecule, one instant, just to simulate that. So, it's completely out of the range of anything we're going to do with classical computers. But with quantum computing, where we now are building on the principles of quantum mechanics, the low-level instruction set, instead of being things like ands and ors and nots and zeros and ones, we do quantum bits, which are much more powerful and combine in exponential ways. If we had a quantum computer with 160 qubits, we could fit all that information into it. Now, I'm not telling you how we get it in there, and I'm not telling you what we do afterwards. But here's a situation that somehow nature, this tiny molecule, harnesses massive amounts of information. That's philosophy, right? Maybe it's a philosophy of science. But nevertheless, we can harness that and use it in what we call quantum computing.
And of course, we're going to, try to explain that a little bit further. But my first question is, and I've heard, yes and no on both of this. Very, very powerful compared to what we have today. But the question is that type of power, it's a different level or a different type of computing. So the question is quantum computing, or will quantum computing completely replace what we have today? Or are they two different methods to two different problem solving?
So right now, and for at least the next few foreseeable decades, they will be complementary. Quantum computing will not replace traditional computing. And that's simply because the way we know how to create quantum computers today, and a little bit of insight of what it will be like. So think of them, think of the classical computers you have. Again, let me go back to your laptop example.
Sure.
Right? That's a classical computer, and frankly, when you create an app for it, a lot of it is fairly mundane programming, right? You do one thing after another, you do something 10 times, whatever. But every once in a while, whether it's your laptop or your phone or something like this, you want to start, you want to see graphics. You want to draw beautiful graphics. Imagine a video game, right? Things like that. Well, those sorts of calculations to do the graphics are really hard to do. And so people have developed what are called graphical processing units, people like NVIDIA, right? Mm-hmm. And so we have video cards, and that greatly accelerates the math behind being able to draw this beautiful graphics. Think of quantum in the same way in the short term. For certain types of applications, not all, certain problems, certain use cases, and we're still figuring those out, you will use, we hope, a quantum computer, right, to do this. But for the rest of what you're doing, the classical stuff we have right now is fine.
Right.
And even if we roll forward 20 years, so let's say 20 years goes by and quantum computers are much more powerful, more ubiquitous on the cloud. An application you use in business could still be 95% classical. It's just those special bits that you might want to use a quantum computer for.
And hey, very, very true, because being able to mix the two and I guess offload something that, as you said, would be exponentially or infinitely just too complicated for a classical computer, offload that, and then so we're starting to get a good idea of where they're going to fit into our lives. And obviously, IBM as a company, they've really taking a lot of strides in the area of like cloud computing and behind the scenes server management. Is that an area where quantum, obviously, IBM is helping with this research and doing this research, but is this where quantum, like, I guess the question is, people won't really be going to buy a quantum computer in the next 20, 30, 40, 50 years. These machines will be something that will run the infrastructure, the backbone. They'll be elsewhere decentralized, and we'll just kind of get the benefits from using. I assume that's how quantum computers will work. Like, you're not going to have a quantum computer laptop.
Again, not for decades, maybe not for a couple of hundred years. I don't know. Let me know. You're younger than I am. I don't know. No, I think that's right. So, where we are now, you said in your intro, people were waiting and things like this. We've had quantum computers available on the web, on the cloud, for almost 3 years. They went up in May of 2016. So we really are in early days of everything, right? Of the hardware, the software, the system support to put them in data centers and things like that. And we're learning a lot, right? And we're upgrading these things a lot. So it's a period of very rapid innovation across the board.
Right.
Why would you buy something which is going to be obsolete in 6 months? What's your motivation there to do that? It probably makes a whole lot more sense to, as you're learning about quantum computing, as you're experimenting, as you're playing around with algorithms for use cases, access a machine through the cloud that we will upgrade, that we will scale, that we will deal with availability. So you really have to start with all the basic arguments of why cloud computing is a good idea. And then you simply plug in, a quantum computer as an example of something you would access.
I gotcha. Oh, and by the way, if anyone out there would actually like to listen to an interview back in May 4th, 2016, if you want a date, you can go check out the YouTube or wherever podcasts are. We talked to Dr. Andreas Forer, and we talked exactly about this topic. But hey, almost 3 years later, I thought it'd be a good idea to kind of get reacquainted and see where IBM has come with this whole thing. So. And with that being said, we have this question here about IBM's quantum computer in particular. Now, this leads to two questions. One, what kind of quantum computers are IBM's Q devices? And two, does that mean that there are multiple quantum computer, I guess, kind of configurations, or are there multiple types of quantum computers?
There are. And so it goes down to the very question of the quantum device itself. So a qubit, which I mentioned before, this quantum bit, is your basic unit. And it needs to behave like a quantum particle does, right? And so it has to be able to be in various states at different times, what's called superposition. It needs to be able to entangle itself on demand with other quantum particles. And so essentially what you're trying to do is you're trying to build a synthetic atom at the core, right, as a qubit that follows the rules of quantum mechanics in a nice way. You don't use real atoms typically, so you have to simulate them in some way.
Right.
So we use a technology which is called superconducting transmon. Now, that's a mouthful. Now, what it basically means is that superconducting means that there's no resistance, and it also tends, in the wires and such, but it also tends to mean you're very cold. And so our computers operate very close to absolute zero. Absolute zero is zero on what's called the Kelvin scale, which is slightly different from Fahrenheit and Celsius. But at absolute zero, nothing moves. Electrons don't move. We are 0.01 Kelvin above that. Again, to put that in context, outer space is approximately 2.7 degrees Kelvin, which is bitter cold, beyond bitter. And we're much colder than that. So inside one of these quantum computers, it's one of the coldest places in the universe. I mean, by necessity, it's close to absolute zero. And we do that because these quantum devices are very sensitive. They're sensitive to any sort of stray energy that may hit them and interfere with this quantum behavior that we are trying to control. So even if I shone a light, even if I just shone one photon on that device, it would be too warm. It would warm it up, and essentially, in the technical term, it would go wonky, right? It would no longer be predictable in any shape or form. And so ideally, you would completely isolate these things from everybody, right? So you get no interference, there'd be no sound, there'd be no vibration, no light, nothing. It would be in a vacuum. However, having a computer that's isolated from the world entirely is not very useful. So you do, in fact, have to talk to this device. You have to program it. You have to get the results out of it. And so the trick is to build these devices in such a way that you are minimizing this extra noise. And the noise causes errors. So the stage we're in right now is called error mitigation. All the different places, probably more than a dozen, where errors could creep into and disrupt these computations, we're trying to minimize those effects. Sometimes you can get rid of them. Sometimes you have to live with the noise, but you can be kind of clever to get rid of it, right? Let me give you an example. Many people have noise-canceling headphones, right? You look in these open spaces, right, or in airplanes, and people have them. The way they work is they kind of listen to the environment. Maybe the jet engine or something like this. That is, they listen to the external environment, and they subtract some of that noise from what you're hearing to get a purer signal. Well, there are related techniques that you can appreciate that the noise is present, but in some sense subtract it out. So there are hardware and there are software ways of reducing this noise to make them operate better. Now, there are several other techniques that people are experimenting with. There's a technique called trapped ions. There's a technique called quantum dots and so forth. They all have pluses and minuses. We chose this technology, which was primarily developed at Yale University, because we thought a decade ago, and we still think, that it is the technology that we think will scale the best. Mm-hmm. That is, that we'll be able to produce many more high-quality qubits with low enough noise, right? And that we'll be able to produce them in the quantities we need to supply to our clients.
Makes perfect sense. And to put this into something that people can start to play with, and for anyone out there watching the video portion, we've had IBM Research website up, and we poked around far enough that we got to the place where people can run experiments. So this is the exciting part. This is the part where people can get hands-on with this. If you would like to kind of outline why this webpage that we're looking at, the quantumexperience.ng.bluemix.net, the editor, what this is, why it exists, and what people can do with it.
So the first thing I want to tell you, when you said a little bit about this in the beginning, is this word quantum seems magical. I don't know if it's from science fiction or whatever. There was a show when I was younger on called Quantum Leap. It was a science fiction show, which oddly enough, a quantum leap is a big thing, but a quanta is a very small thing. So somebody at some point got very confused about the names there. But this word has been tossed around so many different ways. There was a movie last year, Ant-Man and the Wasp, where there's this funny sequence where they're just calling everything quantum. And the Ant-Man character, Paul Rudd, at some point says, "Do you people just put quantum in front of everything?" There's this attraction, there's this curiosity about quantum computing. And so what we put up, starting in May of 2016, as we said, and evolving since, is a 5-qubit and a 16-qubit machine that people can use. And in particular for the 5-qubit machine, we put up something called the composer. And the idea is that instead of programming in Python or some other language, what we wanted to offer to people was the ability to just drag and drop the different operations, also called gates, onto horizontal lines, and there are 5 of them. So composer, you think of music, right? It kind of looks like that. So you can drag and drop the different gates. Some are single qubit gates, the H gates, the Hanamards. Others are multiple qubit gates, things like C naughts that can cause entanglement. But basically, this fundamental idea of how you would create a quantum circuit at the basic levels is provided by that. And you can build it, and then you have a choice. You can run it on a real quantum computer, or you can simulate it, right? Because for a very small number of qubits, you can have a classical computer somewhat imperfectly pretend to be a quantum computer. So people get a lot of excitement to be able to use it. I've heard of like 6 years old kids playing with it with their parents on it, certainly up through teenagers and beyond that. But it's a way of exploring in a very simple way. Drag things around, see what they do. I will also say, by the way, that we have an app called Hello Quantum, which is available for the iPhone and for Android, and it's a puzzle game. It operates with 2 qubits, and it's for many people, it's addictive, as many puzzle games are. It's a great way of getting introduced to how qubits react and the sort of different things you do to them, what the results would be. So whether it's online or on your phone, we can get you up and running to learn about quantum, and online in particular, you within a few minutes can use a real quantum computer.
Yeah, of course, and we'll include links to this. And now we're checking out the app there. You're right; it definitely looks like a traditional puzzle game, but like you said, base with a base in physics and what we're actually talking about here. So let's deviate just for a quick second. Let's say someone out there is listening to this, and obviously, this is a field that I have yet to hear of a university, maybe Yale or something like that. Like you mentioned, maybe you can specialize in this. But if people out there wanted to get involved in this line of work, is this more math? Is this physics? Is this computer? You mentioned it's kind of a blend of all of them. If you were to recommend, let's pretend you're speaking to the college group of people, which course would you kind of recommend someone go into to start working with this?
So we're in a transition phase where a lot of the classes that you would see would be traditionally in physics departments, moving more to engineering departments, but also with the physical background, right? Now, I'm not a physicist. I'm a mathematician, and I've done a lot of computer science. And one of the reasons why I got involved was I realized that there were very accessible ways of getting into quantum computing. So if you are in physics, and so here let's talk to undergraduates. If you are in physics or engineering, look at what's provided. There's a good chance somehow, some way, something about quantum mechanics, maybe about quantum computing is provided. If you are in mathematics or applied mathematics, the basis there for what you would want to know would be linear algebra, so vector spaces, matrices, things like that. Mm-hmm. Some probability theory, not a lot. You certainly don't have to take a whole course. A few hours will get you up and running. And then complex numbers. And you don't necessarily have to do complex analysis. You just have to be comfortable with the algebra and geometry of complex numbers. Now, given that, there are several very good textbooks that you could jump in and use, but that's enough to kind of start understanding like what a qubit is and what you can do to a qubit and how they interact with each other as well. Now, let me tell you my hope here.
Sure.
My hope, and this, my thinking has changed on this. A year and a half ago, I would have said, I want to see a lot of semester and year-long classes about quantum computing. Those would be nice. Now, you can get some online. So MIT has a very good edX program that you can go and learn really everything you ever need to know about quantum computing. We highly recommend that. They also have a new edX class about quantum computing and machine learning, if you're more AI.
And actually, Dr. Suter, if you don't mind, we're about to run into a commercial break. Would you mind staying over so we can finish our conversation on the other side of the break?
Sure.
Perfect. So, everyone, we're talking to Dr. Bob Suter. He is the Vice President of IBM Q Strategy and Ecosystem, talking everything quantum computers. And when we come back, we're going to talk about how to get into the field and more. Everyone, be right back. Computer America. Stay tuned.
Greece is cheap.
But the airfare costs a fortune.
Paris?
Not much closer, and again, airfare...
What about Puerto Vallarta?
Let's face it, flying anywhere is just too expensive.
Wait, what's this? Low-cost airlines.
With one call to low-cost airlines, you'll drastically slash your travel costs. We're talking insanely low airline prices to any of your favorite destinations. Where would you like to go? London, Rome, Costa Rica, Australia?
Wow, that's cheap.
So why wait? Call now to learn how crazy cheap it is to fly anywhere in the U.S. or international. Our prices are so low, we can't publish them. The only way to get them is to call to instantly hear the most amazing best deals on airline travel. It's that easy. So call now and start packing.
800-215-4461. 800-215-4461. 800-215-4461. That's 800-215-4461.
We are all Brother Wolf. 10 years ago, a group of locals banded together to create positive change. We took animals into our homes, held adoption events at local retailers, and talked to the community about our mission to help build a no-kill Asheville. A decade later, we have achieved so many victories for animals in need. There's been so much progress, yet there's still so much to do. As part of our year-long celebration, we encourage you to become a member of our special Compassionate Circle program. With a monthly donation of $10 or more, you will have behind-the-scenes access to the work we are doing at Brother Wolf. Our goal is to reach 1,000 members because we receive no government funding. Working together, we can help build and sustain no-kill communities. Learn more at compassionatecircle.bwar.org. We are a 501c3 tax-deductible organization.
And welcome back to the Computer America Show, 32 minutes past the hour as we continue on here. And everyone, if you've missed any part of our conversation so far, or probably like me, if you need to go back, rewind, listen to it again, then hey, we certainly make that possible wherever podcasts are heard. Search Computer America, and hey, you should be good to go. We should pop right up. So everyone, we are talking to IBM, and more specifically, Dr. Bob Suter, and Vice President of IBM Q Strategy and Ecosystem. And just before the break, before we had to go to commercial, Dr. Suter, you were talking about, how ideally, you said a little while ago, full-blown courses, but now the information, if you so choose, through resources like MIT or just, out there, you can find a lot of information about this, but please finish your thought.
Sure. And so let me just speak directly to college professors, lecturers, and even high school science teachers, right? That is, quantum computing is going to be phasing into our lives over the next few years and decades. You got to start teaching about this. Now, if you're in college, as I was saying, there are courses in physics and engineering, classes more about the hardware, the computer architecture. But look to supplement existing classes. Right? So if you're teaching a linear algebra class, teach some of the elements of the basis of what a qubit is. Computer architecture, again, if you're talking about traditional classical computer architecture, supplement it by the way for a couple of hours that people are building real quantum computers. That is the architecture of those things. Even business schools, there are a number of use cases people are looking at, new algorithms to do risk evaluation, right? Teach those. So start feeding in the minds of your students the different use cases, the techniques, and how quantum will become more and more useful over time. Because it's the students today who will be in the workforce in the 2020s when we hope to really see some demonstrated quantum advantage. That is, places where we can say, right here, we can show that quantum computing is significantly faster than anything we can do classically. So sneak it in there.
Right.
One or two lectures, wherever it seems to make sense.
I gotcha. Now, of course, you're here, and like all of this is still the latest stuff. But as I understand it, you have something a little bit newer, and this is the IBM Q System One. I am not familiar with this, so I apologize. But could you talk to that?
So, when you approach a topic like quantum computing, as we've discussed, you can do it from so many different angles. So let's look at the three main areas. The first one is the hardware, right? And so here, as we talked about before, how do you make that actual quantum device? Is it superconducting, transmon, something else? What's the physics? What's the engineering of doing that? Another level is software, right? What is the complete software stack? What is the low-level access to the hardware? What's the intermediate level? And what's the high-level library access to make it easier for people to write applications? And this is QuizKit, as I mentioned before, our open-source platform here. But the third level is systems. And this is an outside-in, right, topic to look at. So here what you need to imagine is, as we move forward, that these quantum computers are going to be sitting in cloud data centers. And we have those already, and as I've said, for close to 3 years here. Now, what does it mean to have computer systems available in the cloud? You probably have more than one of them. If it's your cloud data center, you want these systems to be maintainable. You need system software to handle load distribution. You need appropriate security. You need to create enough of these computers to be able to upgrade them quickly. So this is a systems engineering outside-in approach, which says, yes, I've got a quantum computer, but I need to deal with all these other issues as well to make them available. That is, to move a quantum device outside the lab and into the cloud data center. So we set about in late 2017 to design such a quantum system. So before I very carefully talked about quantum device. It's the small chip, it's less than an inch by an inch, but that has all the qubits in it. But what does the full system look like, right? That we can do all these things like stability and security and scalability and so forth. What we ultimately announced in December, in January at CES, was the IBM Q System One. So, starting with the device, moving up into the electronics, into the refrigeration, into the environment in which everything is contained, all the individual components are optimized, but then they're optimized to work together better. Right? If you compare this to our previous model of that we still have running in the lab, the System One can be put together in 10% of the time it used to take us to do previously. It takes up 1/3 of the floor space. So if you're thinking of a data center, floor space is important, as well as power and things like this. So again, this notion of quantum computing, I think when people look at it, they focus on just one little part of it. But we in IBM Q look at all aspects of it, right? Some people use the word holistic, right? Mm-hmm. Everything that has to be involved to building and deploying these systems. And that's what the System One is about. It's really the prototype and the blueprint for how we will start to deploy many of these systems to clients and to students and to researchers.
Yeah, and obviously we are checking out some of the pictures and some of the video that you have available. And seeing your guys put this thing together, it's a lot of heavy steel, a lot of heavy glass, and man, you say 10%. I can't imagine how long the first one must have taken. This is quite the engineering feat you have here.
Well, you make things more modular, right? You start standardizing the parts. For example, with the electronics, we have to create those ourselves. Our quantum computers are programmed with microwave pulses. Now, don't think of a microwave oven. Just think of it as, a certain frequency of an electronic signal that's going through there. You can't just go into a computer shop and get quantum computer, microwave pulse generators. So we build those ourselves. We go through generations of them. We use engineers from across IBM, different parts of IBM, to do that. So we've modularized, well, you know the word I'm trying to say, modularized the system to make it easier to replace the parts. And so what used to take us days or sometimes weeks to redo now takes us hours or days. And this is further evolution, right? And so when we talk about evolving the system, it's not just the quantum chip. It's all these other things we've had to learn to do to make it available. And that's why I think this is important. And I think that, right now we say we're in this quantum ready phase. That is, we're getting ready and making machines that are more powerful to eventually get to quantum advantage. I think the IBM Q System One represents the beginning of the second phase of quantum ready, where people are now saying, it's not just a lab experiment. We really have to deploy these things, and these are the considerations.
Right, and I was going to make a joke about, this is kind of like the most complex IKEA ready to go package that you can. All the parts are kind of modular, but no, this is about on par with what I've experienced with IKEA. So it's you've really, I think, got it to the point where obviously, part 1 or 1,253 goes out. You can order a new part and just kind of slap it in. It's that's an important part of course, integrating these things into businesses. And I think that's a good next kind of jumping off point, which is if you can start, shipping out these IBM Q System Ones, and when you do, who's really going to be interested in buying these things? And you don't have to give me a full customer list right now, but we've heard a lot of interesting things about weather prediction and weather modeling. Which industries do you think are really going to start to gravitate to these things first?
And just to be clear, these are not to be purchased for on-premise. They'll be used on the cloud, right? So the question really is, what sorts of people will be using this? So we have a program called the IBM Q Network, which now consists of 45 different organizations. And some of them are banks like J.P. Morgan, right? Daimler. Last month we announced ExxonMobil is joining. We have universities. We have startups there. We have a number of direct partners as well. The three main areas that I want people to focus on is chemistry and all the related fields there. So material science. So materials can range, let's say at the top end, from new alloys, right, for aircraft, all the way down to lotions and shampoos, really. For new catalysts, for oil and gas, right, for being able to produce new products in a much more energy efficient way. AI is another area. And really three parts of AI, which I'll use as an example. The smallest part is saying, look, somewhere down deep in what you're doing now, there's some math calculation. Can we somehow speed up that one math calculation? Second area is to say, well, there's really a subcomponent of what we do in our AI process today. Can we keep doing what we're doing generally, but just that one subcomponent, so bigger than a calculation, right? But really something that has a defined function. Can we replace that with something with quantum? And then the big part is, can we somehow use these properties of quantum computing, things like entanglement, to really replace the old process entirely and do it much more efficiently and much more accurately? And then the last area is financial services. So to do risk analyses, right? Options pricing, a general replacement for what are called Monte Carlo methods, where we're doing lots of different samples to build a model, let's say, for which financial instruments can live, right? And then you can get an idea of how they might behave. That, it turns out, has other applications. Monte Carlo, it has weather applications. It turns out that the U.S. Coast Guard estimates where ships are using Monte Carlo methods as well. So we can look from an industry perspective, right? But then we can also say, hey, we've got this great tool, this great algorithm that might work several different places. So we're approaching it from all these different dimensions.
Right. No, you obviously you shouldn't limit yourself by just what it kind of can replace. But at the same time, this is another question that we have here, which is what is it going to be able to do that we just can't do now? Because replacing industry, that's great and all, or I should say, revolutionizing industry is great and all. But what happens when you create new fields, new areas, and new products? Is there anything that you're really excited about that maybe isn't possible to, because everything you just listed, is what we're doing now, just much more cumbersome. Is there anything that you're excited about that maybe, just doesn't exist today because of the limits?
Well, when you say cumbersome, I would rephrase that as that the things that perhaps where we will be applying this, either the current results are too accurate or too slow to be nearly as useful as they should be, right? And so that's a huge improvement, right? I think we're going to find that there have been some places, for example, approximating chemical behavior on a computer has been extremely limited to very small molecules. Mm-hmm. And so there are going to be areas of what we'll call quantum chemistry that people have just not done, right? Because the computer is high performance or otherwise. They've just all decided, don't go there, right? And so you'll see it start to phase in that way, right? Consumers won't necessarily know that, right? They don't often know what is the lowest level of computing in what they do. So that's where I think probably we'll see it is across these different fields, areas where people have just stayed away, right? Different types of algorithms, different types of calculations that will, we hope, become more accessible, right? More tractable with quantum computing.
Makes perfect sense. And before we say goodbye, Dr. Suter, I wanted to give you a chance that, so far we, I think, have done a good job of, kind of following you through the website, over at research.ibm.com. We're going to throw links everywhere, including how to run your own quantum experiments and things like that. But I wanted to pose you the question, of course, if people want to find out more, where's the best place to go?
So start with the IBM Q experience. You've mentioned that before. It's easy to find on the web. We have lots of videos, lots of ways of getting into this. On YouTube, there is a video that my colleague Talia Gershon did with Wired last year. And she explains quantum computing to 5 people, starting from, I think, a 6 or 7-year-old, going all the way up to a retired physics professor. She's had well over 3 million views, and many people have told me it's the best video they've ever seen to explain it. So start there. We and others have other videos. Let me say it's a really interesting new area. I think through programs like this, through some recent articles, people are learning better how to explain this. It's really not that scary. And let me leave you with the thought that if nature really operates with quantum mechanics and quantum computing operates according to the laws of quantum mechanics, maybe that's the right way, in fact, of doing computing. And all this other stuff we're doing, right, laptops, phones, and everything, maybe that's just some weird approximation that we've come up with. So things will evolve in very interesting ways over the next years and decades.
If you are excited about this, then I think everyone else out there should be excited about this. And and again, it's been a couple years since I think IBM first introduced us to to this whole idea, and it's really good to see IBM is continuing to do this, and lots of partners. So I'm really looking forward to what's going to happen in the future. And I will say, Dr. Bob Suter, thank you so much for coming out to Computer America and explaining this to us. It was very informative.
My pleasure. Thank you.
All right, our pleasure. And Chris in the background, thank you so much for setting this up. And IBM, of course, thank you for doing everything that you do here. So Dr. Suter, until next time, and IBM, thank you so much for being on the show, and have a great day. All right, and there they go. So everyone, we're going to go ahead and finish up Computer America here. We're going to do computer and technology news as we say goodbye to IBM, and a great segment. Everyone, one more time, if you miss any part of our conversation so far, you can check out the podcast after the show, computeramerica.com, and you can listen to the whole thing right there. So there you have it. All right, and we're going to say goodbye to them right now. Okay, everyone, thank you for joining us through that. That was a lot of fun, very, very interesting segment. And if you want to find out more, computeramerica.com, in the show notes, we'll have a link to all these websites, everything right there. But in these last couple of minutes, we're going to do something a little bit more, I don't even want to say down to earth, because that implies that what we just talked about isn't applicable or, kind of practical, because it is. It's available today. But maybe a bit more consumer focused. And we have a lot of different articles here. We're going to go ahead and jump through some of these. So here we go. Computer and technology news brought to you by Computer America. Lots of different articles, but I think we're going to go ahead and go with rumors, something a little, something a little bit lighter. And Samsung Galaxy S10. You know them. That is the new flagship phone that Samsung was planning to debut at the end of February, where, it's, of course, the S9. Everyone knows about that. Now the S10, and this is supposed to come with a lot of new innovative features. Not foldable, so just to be very clear here, not foldable. But at the same time, it was supposed to be, it was supposed to be a big reveal. Well, turns out there's a leak. Yes, there's a leak, and you can see the video here. We're going to play this, and it's on mute, but it's obviously, I believe this is Swedish. Norwegian. There we go. So Norwegian. And there's leaks where maybe a document gets scanned and uploaded surreptitiously, and you have to kind of say, well, where did this come from, and is it real or not? This leak is the actual 30-second commercial of the Samsung Galaxy S10. And ladies and gentlemen, I have held to this theory for the past couple of years. These leaks that these tech companies do, just like, let's say, I think it was like the iPhone 5S when it was caught, it was leaked in the wild, where one of the developers left it on a bar, and, it was able to get out there. They did like a tear down and things like that. All a PR move. And I think this one is too, but we're going to fall for it. We're going to jump right into it. This is an article from Engadget, and saying that who needs leakers when Samsung is outing its unpacked lineup itself. So I guess unpacked is the event where they were going to display the S10. But here we are talking about the commercial. Ahead of its flagship event tomorrow, so there you go. So probably today. The Korean tech giant has let slip another look at its AirPod-style Galaxy Buds and Galaxy S10. If you thought it couldn't top its earlier leak with the Galaxy Watch app, which we will also be talking in just a second, this time the product were the stars of a full-blown ad aired in Norway's leading commercial TV channel. That's right. The thing got released early. There you have it. So a viewer uploaded a 30-second snippet of the promo on YouTube. According to The Verge, it offers a close-up of the upcoming smartphone that seemingly confirms some of the headline features, including its hole punch display, which you can, kind of see it here. We're going to make the image a little bit bigger. And yeah, essentially front to back, side to side, this phone is... I shouldn't say front to back, but side to side, top to bottom, and other than like a camera hole at the top, you get the whole screen. Like there's only like a little place for the camera lenses to poke out of. It's really impressive, including a rear triple camera setup and reverse wireless charging. So yes, wireless charging is still a thing. Samsung Galaxy Bud emerged toward the end of the video, ensconced in their all-white charging case. The clip also reveals that you can charge the wireless buds by placing them on the back of the Galaxy S10. So not only can the Galaxy S10 receive a charge wirelessly, but it can give a charge wirelessly to the Galaxy Buds. So there you go. Samsung is expected to unveil at least 3 smartphones at the Unpacked event. So earlier today, including its much hyped foldable handset. Chances are we'll see a Galaxy Spot smartwatch too, and maybe even an update to the Galaxy Home. Everyone, of course, will know more, when it actually happens. But there you have it. Now, there's that one, and I think I had another one here, but I think we're just gonna move on to another leak. There was a leak with the Samsung smartwatch. Let's put it this way. Samsung worked overtime, leaking everything before the actual event. And that's okay because, hey, everyone's talking about them now. So there you have it. So there's that article. And then this other leak that we want to talk about. NVIDIA may have done it themselves. NVIDIA may have unwittingly leaked Unity ray tracing support. Now, of course, we have talked about ray tracing before with Darius Jarakshani. It's a very interesting, process to make things look almost photorealistic, almost pre-rendered, things like that when it comes to live gameplay, cinematics. It's going to push the look of video games to the next level. This is going to be the technology that makes it possible. Now, NVIDIA launched the era of ray tracing about 5 months ago with the release of the RTX 2080 Ti. But so far, it hasn't gone over well. I would say, they said that just one game supports it. That's obvious. Why would a development studio bother making a game for something that only has only a handful of graphics cards that can actually support this? No, as it becomes an industry standard, trust me, the industry wants to be able to use this technology. It's just it's not something that's just going to go away. This is something that everyone wants. It's just they're waiting until more people can actually utilize it. So NVIDIA's CEO Jensen Huang was eager to mention that ray tracing support was available in both Unity and Unreal, the most popular gaming engines. The problem is, Unity has yet to reveal anything like that. So, NVIDIA may have just inadvertently stolen its thunder. And for those of you out there who maybe aren't up to date with your video games, let's just go ahead and say that when you talk about Unity and Unreal, the game engines, a massive, massive portion of video games run on both of these. It's because they're free up until a certain point, and then you have to start paying for it. But it's a cost-effective way to get your game off the ground, up and running, rather than creating your own infrastructure backbone basis for your video game. You can, of course, use Unity or Unreal and get a lot of assets, make your own assets, and of course, just get things up and running. So that's why it's so important that Unity is going to be supporting ray tracing. Is that a lot of these games, hey, maybe, if they can make it as simple as, just a couple of hours of additional development in Unity to apply ray tracing, then suddenly that one game could turn into thousands of games that support ray tracing. They said that Unity has its own history with ray tracing, having experimented with it back in 2015. It also teamed with District 9 director. Turn that down just a little bit. There we go. District 9 director in 2017 created an animated series called Atom. It used effects like area lights and volumetric fog, and rendered everything in real time, showing the potential for more realism in gaming. Now, everyone, that's all we have time for today. I want to once again thank our guest, IBM, for joining us on the program. It was a lot of fun, and if you missed any part of it, computeramerica.com. That will be the number one place that you want to go when it comes to any links that you want to hear about, if you want to run your own quantum experiments, if you want to check out any articles that we discuss. everything will be at computeramerica.com. Everyone, have a great day. Thank you so much for tuning in, and we look forward to catching you here next time. So tomorrow on the program, if everything goes according to plan, which you know it always does. Let's see. So if everything goes according to plan, we are looking at a possible Marcel Gagne all Linux show, Cooking with Linux. Everyone, catch you then. Bye-bye.